Hello, welcome back. We're going to continue looking at examples from momentum and energy conservation. And so if you didn't watch the first video, maybe go back and watch that where I went through problems 1 through 3. A lot of these are going to feel kind of similar to that. And so today I want you guys to do a little bit more practice as we're going through these. Take some time to stop and pause the video and think about what you would do next in terms of the problem solving it. And hopefully that'll give you, a better idea when you actually have to do them yourselves. You'll know how to approach these types of problems. All right, without further ado, let's go ahead and get started. So on problem number 4 here, let's go ahead and just read it and see what's happening. So it says an 8-gram bullet, 0.008 kilogram bullet, suddenly shot into a 4-kilogram block that is at rest on a frictionless surface. The bullet remains lodged in the block, which then moves against an uncompressed spring and compresses it by 3.7 centimeters. If the spring constant of the spring is 2,500 newtons per meter, what was the initial speed of the bullet immediately before impacting the block? So hopefully, you have an idea of what the 3 stages of the picture would be. That's how I like to break down these problems. So let's look at just, stage 1, where we have the block, the uncompressed spring here, and the bullet flying toward the block. And we call this stage 1. And now stage 2 is after the collision. So stage 1 is before the collision. Stage 2 is after the collision, where the bullet embeds itself inside the block. But the spring doesn't move yet. And so in both 1 and 2, we have some velocity. And then finally, part 3 is when now the bullet and the block compress the spring here against the wall, and they come to a rest. So we're going to call the velocity here that we're looking for v1. Well, in this case, this is actually what we're looking for in the problem. Here we're going to call this velocity 2, which we also don't know. And then here we know v3 is going to be 0 as the system comes to rest. What we do know about this is they tell us that the spring is compressed. So if I look at just picture 3, the spring is compressed 3.7 centimeters, 0.037 meters. And that's important to note. They give us this K value down here of 2,500 newtons per meter. So that's all the information that we need to figure out the energy of the spring here. Here what's our mass? Well, it's the combined mass of the bullet and the block. So moving together, so we have 4-kilogram block, 0.08. So this mass here we're going to use is 4.008 kilograms. Velocity, we're going to try and solve for that. And this is the information we need for the kinetic energy as well as the momentum. And then finally, here we have, V1, which we're ultimately trying to find. Here, the velocity of the block is 0. So we don't need to worry about the momentum of that. And so hopefully once you get this set up, you can think, okay, so which order do I need to go in? Do I need to go 1 to 2 to 3, or do I need to go from 3 to 2 to 1? And so you'll see the unknown that we're looking for is in phase 1, and this is typically an indication that we should start with part 3 and work backwards. So we're going to go ahead and do that. Now, when I go from 3 to 2, the question comes up is, should I use momentum conservation or should I use energy conservation? And again, we have a spring that's changing shape here, so energy conservation is probably a good idea. There is not really a good way to do this with momentum, because here the energy is being absorbed. We have something exerting a force on the block, and so momentum is not conserved between these two places. This isn't a closed, isolated system between 2 and 3. Between 1 and 2, momentum is conserved. There's no external forces, just internal forces between the objects interacting. So 3 to 2, we're going to use energy conservation. And so let's just think about that. Maybe, now would be a good time to pause the video and write down what you think the equation should be for energy conservation. And so hopefully you got something like this. We have kinetic energy at part 2, and that should equal our spring potential at part 3. And so just writing out the equations for each of these, 1/2 mv squared equals 1/2 kx squared. Mass here is 4.008. Velocity is what we're looking for, so I'm going to write that as v2. And k is 2500. And x is 0.037. Remember to always convert these to meters. Don't forget your square there. Go ahead and plug this into your calculator, solve it out. You should get a velocity v2 of 0.92 meters per second. Now, if we go so now we have the velocity at 0.2, and now we can go from 2 to 1 using momentum conservation. And we're looking at the momentum of the bullet initially and the momentum of the block and the bullet together finally. So, again, you could pause the video, see if you could work the rest of this problem out. And when you think you have a solution, you can, resume and see if you got what I got. Our initial momentum is going to be the momentum of the bullet, which is 0.008, forgetting the other 0, times its velocity, which is going to be our unknown that we're looking for. Now, again, I could write in mass of the block 4 times velocity of the block 0 here, just to show that I am considering the momentum of the block in this case, but 4 times 0 is going to give me 0, and so this is just going to go away as a term. So if you want to write it, you can. You certainly don't have to. And then here we have the momentum at 0.2, which is going to be the 4.008 times v2, which we solved was 0.92. So I'm going to try and write this in here. Zoom out a little bit. All right, so 4.008 times 0.92, our velocity we found there. All right, and so multiply those together, divide by 0.008, and you should find that v1 is this number, 460.9 or 461 meters per second. All right, and again, so that's the way to solve these problems out. Draw your kind of 3 phases and then figure out, do I got to go from 1 to 2 to 3, or do I got to go from 3 to 2 to 1? When I go from 1 to 2, am I using momentum or conservation of energy? When I go from 2 to 3, am I using conservation momentum or conservation energy? Once you can answer all those questions, you know how to set it up, and then it's just the algebra. All right, so a couple more examples. Here we have a 25 kilogram piece of clay moving 500 meters per second. It impacts and sticks to a wooden block with a mass of 25 kilograms. How much work must be done to the clay block combination to bring it to rest after the collision? So here, I'm just trying to bring back a few concepts we talked about before, which is this idea of work. And hopefully you remember from the unit on work that work equals change in kinetic energy. And so I can say KE final minus KE initial. And that's kind of what I'm looking for. So this is going to answer the question. It comes to rest after the collision, so I know that final velocity will be 0. So let's kind of look at what a picture of this might look like. So we have the clay. There's the clay, 25 kilograms. It's quite heavy. Moving at 500 meters per second. That is a big, fast-moving piece of clay. Probably would have been launched from some sort of a trebuchet type apparatus. I don't even know actually how it would be getting that fast. These numbers are insane. Anyway, yeah, you'd have to have some serious firepower to fire something that massive that quickly. Anyway, we have a poor 25 kilogram wooden block. Probably just shatter from this impact, to be honest. But we're gonna make the assumption that it doesn't. Okay, so this is gonna bring into a collision with this guy, and these things are going to combine. Clay is gonna hit the wooden block, and they're gonna stick together, and they're gonna move off with some V2. Again, this is 1, this is 2, and then our final picture is going to be basically this idea that after some point there has to be some work being done, probably from friction or some other things that are applying a force to the left on this thing as it stops. It's going to be negative work as this thing goes to 0. All right, and this would be point 3. So again, you should see, okay, from point 1 to point 2, I'm going to have momentum conservation. From point 2 to 3, I'm going to have some energy conservation. In this case, well, not energy conservation because work's being done. So we're going to have some energy loss. So let's start from 1 to 2. How do I know to start from 1 to 2? They give us all the information that we have in part 1 to get the answer to part 2. So that's a good place to start. And that's what we're going to be looking for. So if you want to go ahead and see if you can write out the equation, now's a good time to do that. And hopefully you got something like this. Again, you don't have to write this 25 times 0 piece, but if you did, then that's fine. And now we have the combined mass of 25 plus 25 going at a speed of v2. And so if I solve for v2, I'm going to get a v2 of half of what it was before, or 250 meters per second. Intuitively, this makes sense. I have equal massed objects, and so the velocity will be half after the collision of the two objects moving together. It's still moving pretty quickly here. All right, so how do I finish this off? Now, this part's going to be a little bit different than the previous examples, but still doable. Thinking about this work equals change in kinetic energy. So all I'm going to really do is say, okay, well, I know the amount of work that I need to do is going to be equal to KE final minus KE initial. And so I have this 1/2 MV final squared. Remember that this I'm calling final. This I'm calling initial. The mass of them are going to be the combined mass in both cases, 50 kilograms. V final is our 0, V3. So this whole term actually is just going to go away, minus 1/2 50, and then velocity of 250 squared. So 25, 1/2 of 50 is 25 times 250 squared. It's going to give you this pretty large amount of energy. And it's going to be negative, let's see, 1,562,500 joules. So quite a bit of energy that's required to stop this thing. And this is just because of the insane amount of velocity that this thing has and for how massive it is. Yeah, this is kind of an unreasonable problem to actually think about doing in real life. But yeah, this amount of energy, that's a lot of energy. a lot of energy. All right, moving on. And this will be our final problem for today. All right, so in example 6, it says a 15 gram bullet moving 500 meters per second strikes and becomes embedded within a 1.10 kilogram wooden block on a horizontal surface. If the coefficient of kinetic friction between the block and the surface is 0.25, how far will the block slide after the impact before coming to rest? So here we're just, again, going back to kind of stuff we've talked about before, connecting all the concepts that you should have learned this year. Or at least over the past few months when we've talked about energy and forces and friction and all that good stuff. All right, so the idea here is, once again, our bullet. It is 0.15 kilograms. It's moving at 500 meters per second. It strikes a wooden block, which is at rest on a surface now with friction. So we're not neglecting friction here. When there's friction involved, energy is not conserved. So we're going to have to think about that. What happens, again, this is stage 1. What does stage 2 look like? Well, there's a collision that happens. The box and the bullet embeds itself in the block, and then they move off with some velocity v2. And we have a mass that's combined of 1.115. And then finally, part 3, they're coming to rest. How far will the block slide after the impact before coming to rest? So, it travels some distance, delta x, where the box will then have a velocity of 0. And we want to know, well, how far did it slide? Okay, so again, thinking about the problem and how to solve it, you should be able to answer the question, where do I start? 1 to 2 or 2 to 3? And looking at the information they give us everything for part 1, and so that's where I'm going to start, starting from 1 to 2. And should I use energy conservation or momentum conservation? Well, there's a collision happening, so I want to use conservation of momentum. Again, go ahead and try and write out the equation, pause the video, and hopefully you got mass of the bullet times velocity of the bullet plus mass of the block times velocity of the block, which is 0. And again, I want to write that out. You don't have to. And then that should equal my final mass of the block, 1.115 times v2. And solving for v2 gives 6.73 meters per second. So all pretty standard stuff. All right, now we're going to look at 2 to 3. And again, we're going to ask the question, should I use momentum or energy principles here? Now, here we have friction. And this should be a giveaway that some work is being done. The work of friction is being done to slow this thing down. There's a loss of kinetic energy. And this is what I should be using energy principles. Momentum principles, momentum is not conserved. There's an external force acting on this thing, namely friction, that is causing it to slow down. So momentum doesn't work. Let's use energy principles, specifically not conservation of energy this time because we have friction involved, but work equals changing kinetic energy is a good starting place. So I know the amount of energy that I had here. That's my initial. I know the amount of energy that's going to have final is going to be 0. Thinking about this, KE final is going to be 0. And so I can say, all right, well, work equals KE final, which I know is going to be 0, minus KE initial. And I'll just write this out as 0 minus 1/2 the mass of 1.15 times the velocity of 6.73 squared. So this just gives me an energy amount here that I can grab. Now, what's the left-hand side of the equation? So remember, let me kind of write this off to the side. Come on, eraser. There we go. Remember that work we defined as F times F dot D, force dot with displacement or with delta X, and which can be written as, a vector dot product or F times D times cosine of theta. In this case, let's draw a little free body diagram and see what's happening. We have our normal force, we have gravity, and we have friction that's slowing this thing down. And if I think about it, it's delta x is going to be its distance displacement vector is going to be to the right, friction's to the left. So this should indicate to you that theta is 180 degrees. They're in opposite directions. And this should give us a negative work, which makes sense. All right, our goal is to eventually find the coefficient of, is to find how far the block will impact, or how far the block will slide after impact. So our goal is to figure out what the distance is here. This is a number that we can solve. So the left-hand side here, we got to work out a little bit more to solve for distance. Namely, we need to figure out what the force is. Well, we're looking at the force of friction here. And so hopefully you remember another equation that we used when we talked about friction, which was mu times the normal force. And this coefficient of friction is given as 0.25. What do we know about the normal force? Well, it's got to be equal to the force of gravity. All right, so I'm gonna kind of write all of this down for the work. So the work here is force times distance times -1. That's cosine of 180 is -1. In case you're wondering where I got that from. Distance is what we're looking for. So what's force? Well, force is going to be the force of friction, which is mu times the normal force. And the normal force is going to be equal to the force of gravity, which is m times g. We get this mu mg, that's all force, times distance times -1. And that's going to equal this number on the right-hand side. Further, I can plug this in, 0.25 mu. The mass is going to be our combined mass of the bullet and the block together, 1.115, because friction is slowing down both masses. And then, oops, forgot gravity. Can't forget about 9.8. Distance is unknown, and then -1, and then all of that will equal -1/2. So now I'm bringing the right-hand side of the equation back in. 1.115 times 6.73 squared. Let's bring that back down. And now we get an equation with one unknown. We can solve it. So I'll let you do the math, but working that out, you should find that the distance is 9.2 meters. That's how far this thing is going to travel, given this friction. So actually quite far. All right, and there you have it. So again, in this video, we in these last 2 pages of notes, we've talked a lot about momentum and energy conservation, and momentum and energy principles, and how we can solve a lot of different types of problems using momentum and energy combined. And even in this last example, we threw in energy concepts and force concepts that we learned way back when. And so I'm hoping that you can see how all of this stuff is connected, and how we can use all these concepts working together in order to solve some different problems. So I hope you guys enjoyed this video, and I will give you guys a problem set next week to work on. And until then, I will see you later and have a good weekend.